Hello, it's Keith here, and this is lesson 4 of the ChibiTracks series of my 68070 programming tutorials. This is the last of the ChibiTracks tutorials. We're going to be looking at the last part of my music player's code. What we're going to look at today is the code that calculates the frequencies. Now, at a simple level, this is taken from a lookup table. We have each note in the octave, which is has the various frequencies that we might need to use, but for sharps and flats, these are calculated by basically taking two and dividing them. You can take the C value and the D value, add them together, and you can divide it by 2 and get to C sharp, and we do that for all the sharps and flats. But then beyond that, we want to be able to make more subtle movements between notes, and so what I have is a fractional function which will take a fractional part between one of those values, and so this allows for smoother movements than the values in the lookup table or just a simple divide by 2 can provide. And so I've created this function called fraction 16, which will calculate a fractional point between two 16-bit values, and so it creates 15 between values in a hopefully fairly fast way. So that's what we're going to look at today. So let's go over to the code and let's take a look. Okay, so the function we're looking at today is this so-called tween tone function. Now this is used in ChibiTracks. Whenever we want to update the channel, basically we run the tween tone function, passing to it a note number and also a pitch shift. So D2 is the note number, that's a byte, and D0 is the pitch shift, and this is used by tween tone. So tween tone will now calculate the 16-bit value that we actually pass to the ChibiSound Pro driver. Now, if you need to know how all of that kind of thing works, please see my other tutorials. ChibiSound Pro is a hardware abstraction layer that I've written for each of the systems in my tutorials so that ChibiTracks can work on all of them. So that's the way I've split things out. So the tweener will be executed with D2 containing the note number and D0 containing an offset. Now this offset is in two parts. The top nibble is an actual offset to the note number itself. So this top nibble is basically added to D2. You can actually see that here. We are taking the top nibble, shifting it to the right by 4 bits, and then adding that byte to D2. So D2 is now offset by the 4 bits there. The F is the fractional part between that note and the next note in the lookup table. So this is all going to be used to calculate the frequency that we use, and as I say, the lookup table is platform specific, so there is a lookup table like this for all of the notes in the octaves for each of the systems, and that will give us the value we need. Okay, so tween tone will do that for us, and what it does is it runs this routine called get chibi tone. Now what this does is this will read in the lookup table for the current platform. It will then clear the bottom bit because that is used for the sharp or the flat. Basically setting that to 1 will sharpen a note. Flattening is just the same in the opposite direction. And so each entry in our lookup table is actually 2 bytes. So by clearing that bottom bit, we've actually effectively doubled the number that we want. And so we read in the first 16-bit value from our lookup table here. We read in one of these values, so maybe we've read in C there. So that's what we've done there. And then what we're doing is we're testing the original bit that we cleared here, which is the sharpening bit. Now if that is 0, then actually we just need that basic value we've just read in. So D2 now contains the correct value. So in that case, we just jump down to here and we return. However, if we're actually trying to get a sharp value, what we're going to do is we're actually going to get the next value along as well and divide it by 2. So what we're doing here is we're dividing the first value by 2 there. And then what we're doing is we are reading in a second value from that lookup table. We actually incremented A3 before. So we're now reading in the following value from that lookup table here. We're dividing that value by 2, and then we're adding the 2 together. So if we were trying to get C sharp, we would read in the C value, read in the D value, divide both by 2 and add them together. So that's how we are calculating our value with the tweener. Okay, so that's what get chibi tone does. And so what this is doing here is it's doing the first part of calculating the note, having added the offset at the start here. Now the remaining thing we might want to do is we might want to make a fractional shift from this note to the next note, so from C sharp to D by a fraction of 0 to 15, and so this allows for smoother wavy notes and things like that. Now I've used that to simulate a frequency wave that was done with I think it was done with the envelopes function before on Arcus Tracker, but when I ported my music file from Chibi Akuma's to ChibiTracker Pro, my music tracker, it can't do that. It has no platform specific functionality like that, so I simulated it by just changing the frequency using this function. So anyway, if those bottom bits are 0, then we don't need to do any more, but if they aren't 0, then we need to calculate some kind of fractional shift. So what we're going to do is use get ChibiTone again to read in the following value 1 unit after the previous one. So from C to C sharp to D, and so on. So that's getting the second value that we're trying to shift into by some amount. And then what we're doing is we're running tween 16 HLDE here. And that is what we're going to look at now. So here's tween 16 HLDE. Now HL and DE, the name has been passed on from the Z80 version. The Z80 was the original version. But basically what this will do is it will get a value from D3 to D2 by the fraction in D0, in the nibble in D0, so from 0 to 15. So if D is 0, we would get the whole of D3. And in theory, if D0 was 16, which isn't technically an allowed value, but if we gave it that, we would get the whole of D2. And if we gave it a value of 8, we would get it right in between D3 and D2, and a value of 1 would be almost entirely D3, and so on. So this is giving us a value. It's effectively expanding our lookup table and adding 16 fractional values in between each entry in that lookup table. So that's what we're going to be doing, and that's what this routine does. So the first thing we're doing here is we are basically testing D0. Now, in the case of the code as it's used here, this would never happen because we've already checked this, but I'm making this code portable because, to be honest, lookup tables, like sine tables and things, we often want to simulate a bigger table than we've provided. So I thought making this future-proof was a good idea. So we're checking if the value in D0 is 0, and in that case, we just want to return the value that is already in D3. So in that case, we are just jumping down here and we're returning. Otherwise, what we're going to do is we are going to basically get the fractional part of D2 based in the value within the D0 register. So if the D0 register was 1, then we would get 1/16th of D2 here. What we will then do is we will then get that value back, and we will then negate the value in our D0, and then we will basically get the opposite ones. So basically, if we got 1/16th of D2, we're going to want to get 15/16ths of D3, and that's what we're doing here with fraction 16 here, and then we're adding those two values together, and that will give us our fractional part. Now, basically, this is the fraction 16 routine, and it's effectively doing the formula D3 equals D3 times, open brackets, D0 divided by 16. Now, what we're basically going to do is we are going to basically repeatedly bit shift the value in D3, dividing it by 2, and then we're going to test each of the bits in D0 that matches, and then add to a build-up if that bit matches, and this is effectively doing that division calculation for us. So again, we're checking to see if we've been given a value of 16 or over, which would mean that we want to provide 100% of D3. So the value in D3 is already the correct value. So in that case, we are going to return. We're also checking if D0 is 0, in which case we just want to provide a value of 0, in this case in D3, because we were being asked to provide 0% of D3. So we've got to check for that as well. And then any other value is going to be calculated by this build-up. And so what we're doing here is we are storing D3 and D2. That is the value we're going to be repeatedly dividing. We are then masking to make sure that we've got a valid value there in D2, because this is only working in 16 bits. And then we are clearing D3, which is now going to be our build-up. Now, what we're going to do is we're going to repeatedly divide D2 by 2, and then we're going to test the matching bit within D0. And so here we're effectively halving D2, and then we're testing the bit with the value of 8 here in D0. If that bit is set, we're adding that value, that halved value of D2, to the value in D3, which is our build-up that we cleared to 0. We're then halving D2 again and testing the bit that's got the value of 4 here in D0 and adding it if it applies, and then we're doing the same again, and then we're doing the same again, and so we've effectively potentially added 1/16th, 1/8, 1/4 and 1/2, and so this in total would make up 15/16ths. And because we've tested each of the matching bits in D0, by the time we get to this point here, we have effectively calculated that fractional point, and we've done it in a way only using a short sequence of bit shifts and with no kind of loops. And so this is a fairly, I think it's the most efficient way. It's certainly the most efficient way I know of. This was ported from the Z80 and it's also on the 6502. I think this is the best way of doing this on this system, even though this system does support multiplication and division. I think that this is faster actually. So as I say, this is something I'm hoping to use again if I ever need to do any work with sine tables or any kind of lookup table that is too small for my requirements. You know, especially a big problem on Z80 systems. We don't have much memory, and we might want to have a 256 step sine table but only store 16 bytes. So something like this is quite useful. Anyway, as I've said before, if you like what you've seen, please like and subscribe, but of course also go to the website and download the source code, not just for today's example, but also the ChibiTracks. The ChibiTracker Pro is actually free and open source. It was written in C#, and you can download the source code to it, so you can not just use the program, but you can make it better. If you don't want to make it better, but you want me to make it better, then please consider backing me on Patreon, because as far as I'm concerned, these music tutorials are done. I wrote them because I was planning to make multi-platform games, and I wanted multi-platform music, but I simply don't have the time to do that, so I'm not going to. So if you want to see more work on this music software, please back me on Patreon, because if I'm being paid to do it, I will do, but if I'm not, then my hobbies are going to go other places. Anyway, hope you enjoyed what you've seen. Thanks for watching, and goodbye.